In this video, we will deepen our understanding of integration techniques by solving the same integral in two different ways. We will solve by u-substitution, and we will also solve using some other technique. First, let's find this integral by rewriting it as a memorized trig integral. Cosine squared can be rewritten as cosine x times cosine x. And then we have this sine x in the numerator. I'm going to put it right here. So let's split this apart as two separate fractions. You can see that on the right-hand side we have sine over cosine. On the left side, I'm going to rewrite this as 1 over cosine. So 1 over cosine is the same as secant. So we have the integral of secant x, and we know sine over cosine is tangent. Hopefully you recognize secant tangent as one of our memorized trig integrals. When you perform the integral of secant tangent, you should be asking yourself the derivative of what is equal to secant tangent. And hopefully you know that the derivative of secant is secant tangent. So that means that's the integral. So we simply have secant x plus c, and that's the answer. Let's do the same integral again, this time using u-substitution. I'm looking for an expression that's in some way inside of another function. So I see that we have cosine x squared. So cosine is sort of inside of the squared part. So my guess is let's let u equal cosine x. And then we will also need the derivative of u. Well, let me just say u prime. And the derivative of cosine is negative sine. So we can rewrite this integral in the following way. We have the integral of sine x over. So cosine is now u. So cosine squared will become u squared. We replace dx with du over u prime. So that's du over negative sine x. I'm going to go ahead and take this negative sign and put it out in the front though. So we have this. Right away we notice that we have a sine x in the numerator and a sine x in the denominator. So these will cancel each other out. And I have negative integral 1 over u squared du. Let's rewrite this a little bit. So 1 over u squared is the same as u to the negative 2 power. And now we can use the power rule of integration. So adding 1 to the exponent gives us a negative 1. And then when we divide by this new exponent, it's going to cancel out the negative sign in the front. So we just have u to the negative 1 power plus c. I think I'm going to write this in red. It's my traditions. U to the negative power, the negative 1 power plus c. In other words, I think I'll make a new column. This is 1 over u plus c. So I have 1 over u plus c. And remember, u is cosine x. So I now have 1 over cosine x plus c. But of course, 1 over cosine is secant. So we end up with secant x plus c. And that's the answer. Now compare that with what we got the first time, and of course it is the same. Now let's solve this integral in two ways. First, by simplifying the integrand. So I'm going to rewrite this a little bit. So I have x times the quantity squared, which would be x squared plus 4 times x squared plus 4. Let's go ahead and multiply these out. So I'm going to get the integral of x times, and we have x to the 4th power, all right? 4x squared and 4x squared, when you add those together, you get 8x squared, and then plus 16. Now let's distribute the x, so we get the integral of x to the 5th power plus 8x to the 3rd power plus 16x. Now we can do the power rule and integrate term by term. So I'm going to have x to the 6th power, as I increase this by 1. Dividing by my new exponent, I have 1/6 plus 8 times. Actually, I think I'll just do this sort of automatically. Increasing this exponent by 1, I have 4. And then 8 divided by 4 is 2. Okay, increasing this exponent by 1, I have x squared. And then 16 divided by 2 is 8. And that's it. So let's go ahead and just put the plus c on there. And this is the answer. Let's solve this same integral again, this time by u-substitution. So what do I see that's inside of something? I see the x squared plus 4 that's being squared. So my guess will be, let's let u equal x squared plus 4 and kind of see what happens. In that case, u prime is going to be 2x. So let's rewrite the integral, making that substitution. I have x times u squared. Instead of dx, we will write du divided by u prime, so divided by 2x. I'm going to bring this 2 out to the front as a 1/2 since it is in the denominator. In fact, I'm just going to move it right now. So I have this. And I'm noticing that we have x in the denominator and we have this x right here. So these will cancel each other out. So now I have 1/2 integral of u squared du. So power rule. We have u to the 3rd power, and we need to divide by this new exponent. So if I do 1/2 divided by 3, that's going to be 1/6. And the constant of integration, so plus c. Let's go ahead and put the u back in and kind of see what we have. So we have 1/6 times u cubed. So that'll be x squared plus 4 cubed, and then plus c. So this would be the answer. When we compare this to the previous result, they do not quite look the same. So just for fun, let's expand this out and convince ourselves that they are actually the same. All right, of course, if we were simply finding this integral, we would just find this result and stop. I could expand this as a binomial times a binomial times a binomial, or I could have used Pascal's triangle instead. If you multiply these two factors, you get this trinomial. If you multiply this binomial times this trinomial, you get this polynomial. If you multiply everything by 1/6, in other words, if you divide everything by 6, then you get this. Notice here at the end that 64 divided by 6 is a constant. and a constant plus a constant is just another constant. So I really can just replace this with c. Technically, this is a different c than before, so I should call all the other c's something slightly different like c1. But anyway, you end up with this. Now let's compare with what we got the first time, and you see that it is exactly the same. So, of course, you do not need to do any of this stuff that I just did in purple. This was just for fun to convince ourselves that these are equivalent. If you were really just solving this problem by substitution, you would certainly stop here. This last one is a little bit different. We are actually going to use u-Substitution both times with just different values for u. For part E, let's let u equal tangent x, which means that u prime will equal secant squared x. Let's go ahead and rewrite the integral with that substitution. So instead of tangent x, we now have u. So that's u secant squared x. Instead of dx, we will now write du divided by u prime. So divided by secant squared x. Now we notice that we have secant squared in the numerator and the denominator, so these will cancel each other out. That leaves us with the integral of u du. Raising this, increasing the power by 1, we get u squared. And then dividing by our new power, we have this 1/2 in the front and plus c. Now putting tangent back in, we have 1/2 tangent squared. We have u squared, so it'll be tangent squared x plus c. Kabam! So let's slide on over and do the same problem again, but this time we will let u equal secant x. That means u prime will be secant x tangent x. Let's go ahead and rewrite the integral with the substitution. So we still have tangent x, but then secant squared will become u squared. Instead of dx, we will put du divided by u prime. So divided by secant x tangent x. Well, I am noticing that we have tangent in the denominator and in the numerator, so those will cancel each other out. I'm momentarily worried because the secant x is still here, but let's see what we can do about that. So for now, I have u squared over secant u, not secant u, secant x du. It turns out to be okay that secant x did not cancel out because u equals secant x. So I can put a u here instead. So then I have the integral of u squared over u du. Of course, u squared divided by u is just u. Looking very familiar. Using the power rule of integration, we get 1/2 u squared plus c. And then putting the original value of secant back in, we get 1/2 secant squared x plus c. Kabam! That is the answer. And we're done with that problem. However, we are curious because these look different. We have the tangent squared in this one and the secant squared in this one. So it would be fun to convince ourselves that these are actually the same thing. So for this, we will need our trig identities. One of our Pythagorean identities was that tangent squared x plus 1 equals secant squared. So let's see what happens if we rewrite secant squared and replace it with tangent squared plus 1. So then we will have 1/2 tangent squared x plus 1, and then plus c. All right, I think this is going to be that deal where we end up with a new constant, so I'm going to call this c1. If I distribute the 1/2, then we have 1/2 tangent squared x plus 1/2 plus c1. But of course, this is just another constant. So I could just write 1/2 tangent squared x plus c. So now we see that these are equivalent. They simply have different values of c. And if we look back, we can see that it does match what we got the first time.